Okay, let us continue with the book Deep Reading. Quite apart from conciseness, assignment operators have the advantage that they correspond better to the way people think. We say add 2 to I or increment I by 2, not take I, add 2. When put the result back in I, thus I plus equal 2. In addition, for a complicated expression like this, the assignment operator makes the code easier to understand, since the reader doesn't have to check painstakingly that two long expressions are indeed the same, or to wonder why they're not. And an assignment operator may even help the compiler to produce more efficient code. We have already used the fact that the assignment statement has a value and can occur in expressions. The most common example is like this. Assignments using the other assignment operators plus equal, minus equal, etc. can also occur in expressions, although it is a less frequent occurrence. The type of an assignment expression is the type of its left operand. Exercise 2, middle score 9 in a 2's complement number system. X ampersand parenthesis x minus 1 deletes the rightmost 1 bit in X, Y. Use this observation to write a faster version to bit count. 2.11 Conditional expressions. The statements of course compute in the maximum of A and B, the conditional expression written with the ternary operator question column provides an alternate way to write these and similar constructions in the expression. The expression E1 is evaluated first. If it is non-zero, true, then the expression E2 is evaluated, and that is the value of the conditional expression. Otherwise, E3 is evaluated, and that is the value. Only one of E2 and E3 is evaluated, thus to set Z to the maximum of A and B. It should be noted that the conditional expression is indeed an expression, and it can be used just as any other expression. If E2 and E3 are of different types, the type of the result is determined by the conversion rules discussed earlier in this chapter. For example, if f is a float and n is an int, then the expression is of type double regardless of whether n is positive or not. Parentheses are not necessary around the first expression of a conditional expression, since the precedence of question column is very low, just above assignment. They are advisable anyway. However, since they make the condition part of the expression easier to see, the conditional expression often leads to to succinct code. For example, this loop prints in elements of an array, 10 per line, with each column separated by one blank, and with each line, including the last, terminated by exactly one new line. Like this, a new line is printed after every 10th element, and after the ends, all other elements are followed by one blank. Although this might look tricky, it is instructive to try to write it without the conditional expression. Exercise 2, middle score 10. We write the function lower, which converts uppercase letters to lowercase, with a conditional expression instead of if else. Two point 12. Precedence and order of evaluation. The table below summarizes the rules for precedence and associativity. The table below summarizes the rules for precedence and associativity for the table below summarizes the rules for precedence and associativity. The table below summarizes the rules for precedence and associativity of all operators, including those which we have not yet discussed. Operators on the same line have the same precedence rows and in order of decreasing precedence. So, for example, asterisk, slash, and percent all have the same precedence, which is higher than that of plus and minus. Like this table. The operator arrow and period are used to access numbers of structures. They will be covered in Chapter 6, along with size of an object. Chapter 5 discusses asterisk, indirection, and ampersand, address of. Note that the precedence of the bitwise logical operators ampersand, yield, and bar force below equal and exclusive equal. This implies that bit testing expressions like must be fully parenthesized to give proper results. As mentioned before, expressions involving one of the associative and commutative operators can be rearranged even when parenthesized. In most cases, this makes no difference whatsoever. In situations where it might, explicit temporary variables can be used to force a particular order of evaluation. C, like most languages, does not specify in what order the operands of an operator are evaluated. For example, in a statement like F may be evaluated before G or vice versa. Thus, if either F or G alters an external variable that the other depends on, X can depend on the order of evaluation. Again, intermediate results can be stored in temporary variables to ensure a particular sequence. Similarly, the order in which function arguments are evaluated is not specified, so the statement, like this, can and does produce different results on different machines, depending on whether or not n is incremented before power is called. The solution, of course, is to write Function calls nested assignment statements. An increment and decrement operators cause side effects. Some variable is changed as a byproduct of the evaluation of an expression. In any expression involving side effects, there can be subtle dependencies on the order in which variables taking part in the expression are stored. One unhappy situation is typified by this statement. The question is whether the subscript is the old value of I or the new. The compiler can do this in different ways and generate different answers depending on its interpretation. When side effects assignment to actual variables. Hang on. Takes place is left to the discretion of the compiler, since the best order strongly depends on machine architecture. The moral of this discussion is that writing code which depends on order of evaluation is a bad programming practice in any language. Literally, it is necessary to know what things to avoid, but if you don't know how they are done on various machines, that in nonsense may help to protect you. The C variable length will detect most dependencies on order of evaluation. Chapter 3 Control Flow. The control flow statements of a language specify the order in which computations are done. We have already met the most common control flows constructions of C in earlier examples. Here we will complete the set and be more precise about ones discussed before. (3.1) Statements and blocks. An expression such as x equals 0 or I++ or printf becomes a statement when it is followed by a semicolon, as in. Like this, in C, the semicolon is a statement terminator, rather than a separator as it is in Argo-like languages. The braces are used to group declarations and statements together into a compound statement or block so that they are syntactically equivalent to a single statement. The braces that surround the statements of a function are one obvious example. Braces around multiple statements after an if, else, while, or for are another. Variables can actually be declared inside any block. We will talk about this in chapter 4. There is never a semicolon after the right brace that ends a block. If else, the if else statement is used to make decisions. Formally, the syntax is like this, where the else part is optional. The expression is evaluated. If it is true, That is, if the expression has a non-zero value, statement 1 is done. If it is false, expression is 0, and if there is an else part, statement 2 is, is executed instead. Since an if simply tests the numerical value of an expression, certain coding shortcuts are possible. The most obvious is writing. Sometimes this is a sometimes this is natural and clear. At other times it is cryptic. Because the else part of an if else is optional. There is an ambiguity. There is an ambiguity. There is an ambiguity when an else is emptied from a nested if sequence. This is resolved in the usual way. The else is associated with the closest previous else less if. For example, in like this sentence, the else goes with the inner if. As we have shown by indentation, if that isn't what you want, braces must be used to force the proper association. The ambiguity is especially pernicious in situations like this. The indentation shows an equal. The indentation shows unequivocally. The indentation shows unequivocally what you want, but the compiler doesn't get the message and associates the else with the inner if. This kind of bug can be very hard to find. By the way, notice that there is a semicolon after the equal a in this sentence. This is because grammatically a statement follows the if, and an expression statement like the equal a is always terminated by a semicolon. 3.3 else if the construction is like this. Occurs so often that it is worthy a brief separate discussion. This sequence of ifs is the most general way of writing a multi-way decision. The expressions are evaluated in order. If any expression is true, the statement associated with it is executed, and this terminates the whole chain. The code for each statement is either a single statement or a group in braces. The last else part handles the node of the above, or default case, where none of the other conditions was satisfied. Sometimes there is no explicit action for the default. In that case, the trailing can be emptied, or it may be used for error checking to catch an impossible condition. To illustrate a three-way decision, here is a binary search function that decides if a particular value x occurs in the sorted array V. The elements of V must be in increasing order. The function returns the position, a number between 0 and n plus 1. If x occurs in V and -1, if not. The fundamental decision is whether x is less than, greater than, or equal to the middle element v. At each step, this is a nature for else if. 3.4 Switch. The switch statement is a special multi-way decision maker that tests whether an expression matches one of a number of constant values and branches accordingly. In Chapter 1, we wrote a program to count the occurrences of each digit, white space, and all other characters using a sequence of if, else, if, else. Here is the same program with a switch. So long. So long. The sentence. The switch evaluates the integer expression in parentheses. In this program, the character C and compares its value to all the cases. Each case must be labeled by an integer or character constant or constant expression. If a case matches the expression value, execution starts at that case. The case labeled default is executed if none of the other cases is satisfied. A default is optional if it isn't there and if none of the cases matches. No action at all takes place. Cases and default can occur in any order. Cases must all be different. The break statement causes an intermediate. The break statement causes an immediate exit from the switch because cases serve just as labels. After the code for one case is done, execution falls through to the next unless you take explicit action. To escape, break, and return are the most common ways to leave a switch. A break statement can also be used to force an immediate exit from while, for, and do loops as well, as will be discussed later in this chapter. Falling through cases is a mixed blessing. On the positive side, it allows multiple cases for a single action, as with the blank, tab, or new line in this key example. But it also implies that normally each case must end with a break to prevent falling through to the next. Falling through from one case to another is not robust. Being prone to disintegration, being prone to disintegration when the program is modified, with the exception of multiple labels for a single computation. Fourth rules should be used subroutine. Fourth rules should be used subroutine. Subroutine. Fourth rules should be used subroutine. Fourth rules should be used sparingly. As a matter of good form, put a break after the last case. The default here, even though it is logically unnecessary someday when another case gets added At the end, this bit of defensive programming will save you. Exercise 3, middle score 1. Write a function expand which converts characters like new line and tab into visible escape sequences like \n and \t as it copies the string s to t. Use a switch. 3.5 loops, while and for. We have already encountered the while and for loops in the expression. Hang on. The expression is evaluated if it is non-zero. A statement is executed and the expression is re-evaluated. This cycle continues until expression becomes zero, at which point execution resumes after statement. Here, the for statement is equivalent to like this. Grammatically, these three components of a for are expressions. Most commonly, expression 1 and expression 3 are assignments to function calls, and expression 2 is a relational expression. Any of these three parts can be emptied, although the semicolons must remain. If expression 1 or expression 3 is left out, it is simply dropped from the expression. If the test expression 2 is not present, it is taken as permanently true. So like this is an infinite loop, presumably to be broken by other means, such as a break or return. Whether to use while or for is largely a matter of taste. For example, like this is no initialization or reinitialization, so the while seems most natural. The for is clearly superior when there is a simple initialization and reinitialization, since it keeps the loop control statements close together and visible at the top of the loop. This is most obvious in for, which is the idiom for processing the first n elements of an array. The analog of the fortran or PL/I do loop. The analogy is not perfect. The analogy is not perfect. However, since the limits of a for loop can be altered from within the loop, and the controlling variable I retains its value when the loop terminates for any reason, because the components of the for are arbitrary expressions. Hang on. For loops are not restricted to arithmetic progressions. Nonetheless, it is bad style to force unrelated computations into a for. It is better reserved It is better reserved for loop control operations. As a larger example, here is another version of A to I for converting a string to its numeric equivalent. This is one. This one is more general. It copes with optional leading white space and an optional plus or minus sign. Chapter 4 shows A to F, which does the same conversion for floating point numbers. The basic structure of the program reflects the form of the input. Each step does its part and leaves things in a clean state for the next. The whole process terminates on the first character that could not be part of a number. The advantages of keeping loop control centralized are even more obvious when there are several nested loops. The following function is a shell sort for sorting an array of integers. The basic idea of the shell sort is that in earlier stages, far apart elements are compared rather than adjacent ones. As in simple interchange sorts, this tends to eliminate large amounts of disorder quickly, so later stages have less work to do. The interval between compared elements is gradually decreased to 1, at which point the sort effectively becomes an adjacent interchange method. Like this, there are 3 nested loops. The outermost loop controls the gap between compared elements, shrinking it from n/2 by a factor of 2 each pass until it becomes 0. Hang on. The middle loop compares each pair of elements that is separated by a gap. The innermost loop the innermost loop reverses any that are out of order. Since gap is eventually reduced to 1, all elements are eventually ordered correctly. Notice that the generality of the form makes the outer loop fit the same form as the others, even though it is not an arithmetic progression. One final C operator is the comma, which most often finds use in the for statement. A pair of expressions separated by a comma is evaluated left to right, and the type and value of the result are the type and value of the right operand. Thus, in the for statement, it is possible to place multiple expressions. Multiple expressions in the various parts. For example, to process 2 indices in parallel. This is illustrated in the function reverses, which reverses the string as in place. The commas that separate function arguments, variables, in declarations, etc., are not comma operators and do not guarantee left-to-right evaluation. Exercise 3 middle score 2. Write a function expand which expands shorthand notations like A to Z in the string S1 into the equivalent complete list ABC until XYZ in S2. Although for letters of either case and digits, and be prepared to handle cases like A to B to C and A to Z 0 to 9 and to A to Z. A useful convention is that a leading or trailing is taken literally. 3.6 Loops do while. The while and for loops share the desirable attribute of testing the termination condition at the top rather than at the bottom. As we discussed in chapter 1, the third loop in C, the do while tests at the bottom after making each pass through the loop body. The body is always executed at least once. The syntax is like this. The statement is executed. The statement is executed, then expression is evaluated. If it is true, statement is evaluated again, and so on. If the expression becomes false, the loop terminates. As might be expected, do while is much less used than while and for, accounting for perhaps 5% to all loops. Nonetheless, it is from time to time valuable. As in the following function I to A, which confers a number to a character string, the inverse of A to I. The job is slightly more complicated than might be thought at first, because the easy methods of generating the digits generate them in the wrong order. We have chosen to generate the string backwards, then reverse it. The do while is necessary, or at least convenient, since at least one character must be stored in the array S regardless of the value of M. We also use the braces around the single statement that makes up the body of the do while, even though they are unnecessary, so the hasty reader will not mistake the while part for the beginning of a while loop. Exercise 3, middle score 3. In a 2's complement number representation, our version of I to A does not handle the largest negative number, that is, the value of n equal to minus n power word size minus 1. Explain why not modify it to print that value correctly, regardless of the machine it runs on. Exercise 3, middle score 4. Write the analogous function I to B, which converts the assigned integer into a binary character representation in S, while I to H, which converts an integer to hexadecimal representation. Exercise 3, middle score 5. Write a version of I to A which accepts 3 arguments instead of 2. The third argument is a minimum field width. The converted number must be padded with blanks on the left if necessary to make it wide enough. 3.7 Break. It is sometimes convenient to be able to control. It is sometimes convenient to be able to control loop exits other than by testing at the top or bottom. The break statement provides an earlier exit from for, while, and do, just as from switch. A break statement causes the innermost enclosing loop or switch to be excited immediately. The following program removes trailing blanks and tabs from the end of each line of input, using a break to exit from a loop when the rightmost non-blank long tab is found. GetLine returns the length of the line. The inner while loop starts at the last character of line. Recall that "-n decrements n before using the value. This scans backwards, looking for the first character that is not a blank tab or new line. The loop is broken when 1 is found, or when n becomes negative. That is when the entire line has been scanned. You should verify that this is correct behavior even when the line contains only whitespace characters. An alternative to break is to put the testing in the loop itself, like this. This is inferior to the previous version because the test is harder to understand. Tests which require a mixture of ampersand, bar, exclusive, or parentheses should generally be avoided. 3.8. Continue. The continue statement is related to a break, but less often used. It causes the next iteration of the enclosing loop for while do to begin. In the while and do, this means that the test part is executed immediately. In the for control passes to the reinitialization step. Continue applies only to loops, not to switch. A continue inside a switch inside a loop causes the next loop iteration. As an example, this fragment processes only positive elements in the array A. Negative values are skipped. The continue statement is often used when the part of the loop that follows is complicated, so that reversing a test and indenting another level would nest the program too deeply. Exercise 3, middle score 6. Write a program which copies its input in its output. Write a program which copies its input to its output, except that it prints only one instance for each group of adjacent identical lines. This is a simple version of the Unix Autodidactism Unix. 3.9 Go-tos and labels. C provides the infinitely abusable go-to statement and labels to branch to. Form needs go-to is never necessary, and in practice it is almost always easy to write code without it. We have not used go-to in this book. Nonetheless, we will suggest a few situations where go-tos may find a place. The most common use is to abandon processing in some deeply nested structure, such as breaking out of two loops at once. The break statement cannot be used directly since it leaves only the innermost loop. Thus, This organization is handy if the error handling code is non-trivial, and if errors can occur in several places. A label has the same form as a variable name and is followed by a column. It can be attached to any statement in the same function as in the goto. Is another example, consider the program of finding the first negative element in a two-dimensional array. Multidimensional arrays are discussed in Chapter 5. One possibility is code involving a goto can always be written without one, though perhaps at the price of some repeated tests or an extra variable. For example, the array search becomes. Although we are not dogmatic about the matter, it does seem that goto statements should be used sparingly. If at all. What? Chapter 3 is so short? Chapter 4. Functions in programmed structure. Functions break large computing tasks. Functions break large computing tasks into smaller ones and enable people to build on what others have done instead of starting over from scratch. Appropriate functions can often hide details of operation from parts of the program that don't need to know about them. That's clarifying the whole and easing the pain of making changes. C has been designed to make functions efficient and easy to use. C programs generally consist of numerous small functions rather than a few big ones. A program may reside on one or more source files in any convenient way. The source files may be compiled separately and loaded together, along with previously compiled functions from libraries. We will not go into that process here, since the details vary according to the local system. Most programmers are familiar with library functions for input and output, getchar, putchar, and numerical computations, sin, cos, squared. In this chapter, we will show more about writing new functions. 4.1 Basics. To begin, let us design and write a program to print each line of its input that contains a particular pattern or a string of characters. This is a special case of the Unix utility program grep. For example, searching for the pattern Z in the set of lines. This will produce the output. The basic structure of the job falls neatly into 3 pieces. Although it's certainly possible to put the code for all of these in the main routine, A better way is to use the natural structure to advantage by making each part of a separate function. 3 small pieces are easier to deal with than one big one, because irrelevant details can be buried in the functions. Hang on. And the chance of unwanted interactions minimized, and the pieces may even be useful in their own right. While there is another line, a getLine, a function that we wrote in chapter 1 and printed as printf, which someone has already provided for us. That means we need only write a routine which decides if the line contains an occurrence of the pattern. We can solve that problem. By studying a design from PL/I. The function index returns the position or index in the string S where the string T begins, or -1 if S doesn't contain T. We use 0 rather than 1 as the starting position in S because C arrays begin at position 0. When we later need more sophisticated pattern matching, we only have to replace index. The rest of the code can remain the same. Given this much design, filling in the details of the program is straightforward. Here is the whole thing, so you can see how the pieces fit together. For now, the pattern to be searched for is a literal string in the argument of index, which is not the most general of mechanisms. We will return shortly to a discussion of how to initialize character arrays, and in chapter 5 we'll show how to make the pattern a parameter that is set when the program is run. This is also a new version of getLine. You may find it instructive to compare it to the one in chapter 1. Okay, so long this sentence. Each function has a form like this. As suggested, the various part may be absent. A minimal function is hang on. Which does nothing. A do-nothing function is sometimes useful as a placeholder during program development. The function name may also be preceded by a type if the function returns something other than an integer value. This is the topic of the next section. A program is just a set of individual function definitions. Communication between the functions is, in this case, by arguments and values returned by the functions. It can also be by external variables. The functions can occur in any order on the source file, and the source program can be split into multiple files, so long as no function is split. The return statement is the mechanism for returning a value from the called function to its caller. Any expression can follow return. The calling function is free to ignore the returned value if it wishes. Furthermore, there need be no expression after return. In that case, no value is returned to the caller. Control also returns to the caller with no value when execution falls off the end of the function by reaching the closing right brace. It is not illegal, but probably a sign of trouble. If a function returns a value from one place and no value from another, in any case, the value of a function which does not return 1 is certain to be garbage. The C variable named checks for such errors. The C variable named checks for such errors. Here. The mechanics of how to compile and load a C program which resides on multiple source files vary from one system to the next. On Unix system, for example, the cc command mentioned in Chapter 1 does the job. Suppose that the three functions are on three files called main.c, getLine.c, and index.c. Then command compiles the three files, places in resulting reloadable object code in files main.o, getLine.o, and index.o, and loads them all into an executable file called a.out. If there is an error, say in main.c, that file can be recompiled by itself and the result loaded with the previous object files. With the command, the cc command uses the .c versus .o naming convention to distinguish source files from object files. Exercise 4, middle score 1. Write the function reindex, which returns the position of the rightmost occurrence of t in s or -1 if there is none. 4.2 Functions and returning non-integers. So far, one of our programs has contained any declaration of the type of a function. This is because by default a function is implicitly declared by its appearance in an expression or statement, such as this. If a name which has not been previously declared occurs in an expression and is followed by a left parenthesis, it is declared by context to be a function name. Furthermore, by default, the function is assumed to return an int. Since char promotes to int in expressions, there is no need to declare functions that return char. These assumptions cover the majority of cases, including all of our examples so far. Okay, guys, here is my little break. Go on. Okay, see you, everyone.